Okay, so I thought I'd start this video off with a numerical example of the k-means, just to be sure that everybody's got it. And so in this case we have 5 data points, not very many. I've also plotted them in the plane. I guess I didn't really need that too far. Um, I, I've set the centers randomly to be 0, 1, and 1, 1. And then what do? So our algorithm says sort the data according to the distance function, and then reset the centers and the centroid of each cluster. And so once I know the cluster centers and the data, I've got 5 points and 2 cluster centers, right? So when I take the distance between these two sets, right, I'm going to have 10 distances, right, all together. So for each point, you want to take the distance from each to each center and build a table of those. And so here we have our matrix D, which is 5 by 2. And so, for example, what does the square root of 5 represent? It's the distance from cluster 3, or data point 3 to cluster center 2. So let's double check that. Let's see, 1, 2, 3 is negative 1, 0. And then cluster center 2 is 1, 1. So the distance between minus 1 and 1 is how much? Right, that's 2. And the distance from 0 to 1 is 1. So we get the 2 squared plus 1 squared equals square root of 5. Okay, good. So that's what the distance matrix is all about. And so how do you find the membership function then for all of these? Well, you want the index of the the index of the column with the smallest number. So for example, in this first row, these are the distances, right, from data point 1 to cluster 1 and cluster 2. So therefore, data point 1 belongs to cluster 2 because column 2 has the smaller number. Similarly, the second data point belongs to cluster 1. The third data point also belongs to cluster 1. The fourth data point belongs to cluster 2. And the fifth data point belongs to cluster 1. Good. And so I've put those memberships into a vector over here. And so now I've done the first step. I've sorted the data according to the distance function. By the way, this matrix right here, we're going to be calling the Euclidean distance matrix, or EDM. And this is where a lot of your time is going to be spent on the computer, right? When your computer algorithm is doing k-means, the Euclidean distance matrix is always where the most significant amount of time in your algorithm is usually spent. Good. Okay, so what's next? Excuse me. Okay, and so once you have your Euclidean distance matrix set up, then you can just look for the minimums in each of the rows and figure out what the membership is, and then we go down and reset the clusters, right? So here we have 0, 1, 1, 0, and negative 1, 1 as our new cluster center. Let's see where those are. That's this one. Did I put in 1, 0? There's a negative 1, 0. A negative 1, 0. Yeah. So that one. Oops. That one. The negative 1, 1. So that's one cluster. And then this is the second cluster. Right? And so then our new cluster centers are the means of each of these. And so you can see here, right, the mean of the y value is going to be 0. Mean of the top is negative 2/3. So negative 2/3, 0 is this new cluster center for this one. There's the new cluster center. And then for the other one, it's going to be the average of these 2 points. And so that's going to be 1 and 3/2. And so if we go to 1 3/2, we get that cluster center, right? Good. And now what do we do? Now you go through the same process and do another sort. And by the way, if you sort these data points by which cluster is closer, will the centroid change? Well, it won't if your cluster members stay the same, right? If these cluster members don't change after you've changed your after you've reset your centroids, then you're going to be done, right? Because you'll just be going forever and nothing will change. But in this case, do you see what's going to happen? You might see that, in fact, it looks like this point should belong to this cluster instead of this one. And in fact, that is what happens. And so in our next step then, the resorting will take place, and yeah. once we do the next round, this point does go to this cluster, and then this centroid gets reset, and then it doesn't change after that. So that's a pretty good clustering, I think, for those. And so k-means does a pretty good job, and it's only a two-step process, right? So what we've done is we just sorted the data according to which centroid is closer. We've reset the center using the new data in each centroid, and you just repeat that process over and over again. Good. Okay, and so of course what we've done so far is we've also predefined the value of k, and so you might be asking, well, how might we change that? There are ways to change that to, like let the number of cluster centers grow with the data. But we'll do that, I think, a little bit later. For now, I think this might be a natural place to stop in the notes because, well, there's a couple of coding issues that are going to be coming up. How do I do this in Matlab and Python? So just to let you know where things are, the statistics toolbox is where you'll find the k-means. K-means in Matlab and Octave, or just Matlab. I'll have to double check to see where it is in Octave. Off the top of my head, I can't remember if it's a toolbox that we're going to have to compute, but the k-means algorithm is actually really easy to code. And in fact, if you're a computer science student, you may want to just code your own. And then in Python, so it looks like in Python, the k-means is going to be in the sklearn package. And so we'll have k-means capital K, capital M. Okay. And so I'll have examples of both of those on the class website. Yeah, and then what we haven't talked about so far are some of the pros and cons to k-means. So one issue that might come up, and we'll actually look at this in our data, with some data, is what happens if you have data that looks like a smiley face. So this is like a little data cloud here, a little data cloud here, and this is a little data cloud here. Is k-means going to do a good job with this data set? Well, k-means is going to have a big problem with this, right? It does a really good job with little clusters like that, because remember, k-means is always going to break things up into Voronoi cells. K-means uses Voronoi cells, right? Voronoi cells, gosh darn it, cells to cluster, right, with the cluster center in the middle as the Voronoi center. Of course, you can change that with your metric, but you're not going to be able to get like a shape like this using a Voronoi cell. That's going to be really difficult to do. Of course, it may be that you might get lucky, and so your data might like separate there, and so you might be able to separate it this way. But then you're not going to get this shape to appear very nicely. Okay, so so that's one problem with the k-means. Now one other issue might be density. How does the density affect the clustering? And so we're going to try to answer that in our lab. Okay. Some pros about well, these were cons, right? Pros about k-means is it's quick, well, fairly quick, and easy. So k-means clustering is usually always the go-to. If you're just given a data set, you don't know what to do with it, k-means is probably the first thing that you're going to do with first clustering technique that you would try on it. All right, so I'm going to stop there, and we'll go on to a different method in the next video.